I'm sure that most of you are very familiar with the technique of universal tensile testers. Universal tensile testers are used to investigate solid material like steel, plastic, rubber, composites, and a few of materials more. But at the end of the test, always the materials will be destroyed and will be broken. The method of DMA, dynamic mechanical analysis, is going in a different direction. This technology is a technique which is not destroying the sample after the test. What kind of information we can obtain from DMA? Why high force DMA is mandatory and necessary is I try to explain during my presentation. Over here, I have shown to you typical test frames made for universal tensile testers, UTM testing machines. You see over here, this is the load frame, this is a sample holder, and this is a crossbar moving up and down. This is a similar device. This is a typical appearance of universal tensile testers. DMA equipment looks a little different. Over here, I have shown the low force DMA from NETCH. This is a DMA 242 system. Over here is a large DMA from NETCH GABO instruments. These machines are aimed for the manual testing mode, but in addition, NETCH GABO launched always 15 years ago a system which works as a robot system and is feeding the DMA system with samples out of a magazine for full automatic testing over day and night over the weekend. My name is Horst Deckmann. I hold a diploma in physics and performed my PhD on the field of polymer physics. Time is running. Now I have an experience of more than 20 years in the field of dynamic mechanical analysis. Currently, I'm the technical and sales director of NETCH GABO Instruments, located in Ahlden, the former part of Western Germany. I'm sure you followed up the news in the past. Last year, NETCH and GABO became one company. NETCH GABO is now a proud member of the large NETCH organization. The products we are producing are normally niche products and are able to expand the production range of the production range of NETCH in a wide manner. What we are able to use is a very well established sales organization and a very well established service organization provided by NETCH worldwide. In case you want to communicate with me, you should find on the right side on your screen a field like this. Here you can type in your questions. You can communicate with me directly. I try to reply your answer to your questions, and maybe I do that during the presentation or after the presentation. You always have the chance to send me emails in order to come with your questions directly to me. The title is EPLEXOR, High Force DMA, the Future of DMA. This technology is aimed to investigate a lot of materials, starting from elastomers, polymers, metals, ceramics, composites, fibers, films, and much more. What about the benefit? I try to explain. Let's start about the company first. NETCH GABO is located in the previous part of Western Germany. We are located in the north of Hanover. It's a small village only. Over here you see a helicopter picture done from our facility. The mother company is located in Selb, close to the Czech border. What I try to talk to you about, today. First of all, I want to introduce the instrumentation line, how it works, what's the benefit, what's the difference compared to others. I will show you the principle of operation, how a DMA is working. But last but not least, and I guess very important, is to understand what's the difference between static and dynamic testing, what kind of information I can get out of a dynamic testing procedure. In other words, dynamic testing, but why? Point 4 is the idea, the discussion of the idea of DMA, what kind of information, what physical values I can receive out of a DMA test. In position 5, I want to show you a few sample holder for the high force DMA, and the very mandatory and important part of the presentation is to explain to you why high force are necessary, what is the benefit of high forces and high deformations, what kind of information you get, and what it is good for. And at the end of the day, I will summarize my presentation. Let's start with the instrument line itself. This shows the instrument EPLEXOR 500 is a high force DMA having a capacity of 1,500 Newton for the static and 500 Newton for the dynamic system. The instrument is a two columns instrument. In the center over here is located the oven system. This is a standard oven operating from minus 150 up to plus 500 degrees. Cooling works with liquid nitrogen. Also air chiller systems are available. A second and a third oven system operates up to 1000, respectively up to 1500 degrees C. Behind this cover is located what we call the static drive. This drive is able to adjust a static load on the system, maybe stress, maybe force, maybe strain controlled. Behind the cover over here is located dynamic drive. Dynamic drive is an electrodynamic shaker system. I'm sure that most people are using at their home a stereo system, loudspeaker system, and it's very close to that. Electrodynamic shaker means a coil is embedded in a magnetic, in a magnet, and if you adjust the sinusoidal voltage, this coil is moving up and down sinusoidally. The next figure shows the system after opening the front covers. You see over here, this is the servo motor static load unit. This is a part you already know from universal tensile testers. We call it static load unit. The deformation range of this dynamic system is 50 millimeter from the static side. The load we can superimpose or we can apply with the system is up to 1,500 Newton. This load is available either in compression or in tensile mode. Maybe you can identify over here this small unit. This is a load cell. All our systems, like universal tensile testers, work with exchangeable load cell systems in order to adjust the sensitivity of the instrument to your materials, to your needs. Always this is the chamber, and at the bottom is located the electrodynamic shaker. This is the dynamic drive having a force capability of plus minus 500 Newton, and the total deformation is plus minus 6 millimeter. If you have a look over here, I have summarized these very important key features for you over here. You see, the force range is 1,500 and dynamic range is plus minus 500 Newton. These are the oven systems, 500, 1000 and 1500 degrees C. And the static deformation range is 50 millimeter. Dynamic range is plus minus 6 millimeters. I try to explain to you in my presentation why these large deformation ranges and the large force range is mandatory and necessary for your testing. Now, the principle of operation shall be illustrated in the next overhead. Over here you see the drawing, a principle sketch of the instrumentation. This is again the servo motor. This is a static load unit. This is a static diagrammatic indicator recording the traveling of the static load unit. These are load cells. Over here I have installed the compression sample, and from the bottom, as I discussed already, we superimpose the mechanical oscillation. In the first step, the servo motor is moving down and gives the preload on the sample. This may be a stress, this may be a strain target, or a force target. In the second step, from the shaker, from the bottom, the oscillation is superimposed. It's a movement up and down. You can adjust the frequency. Also, this system can be controlled in terms of stress controlled, strain controlled, or force controlled. The benefit is you are using two independent drives which can be controlled independently from each other. Stress controlled, strain controlled, force controlled, the same can be done over here. This is the dynamic drive, independent. They can be controlled independently. I already mentioned that. And the strong benefit is the exchangeable load cell structure. Load cells with a capacity from 10 Newton up to 5,000 Newton are available. The system has a self-recognition system, so you install the new sensor and the software automatically recognize which load cell, which calibration values are already there. This is the basic idea, so you can adjust the sensitivity according to your materials, to your needs. Now the question is, what is dynamic material testing normally doing? I will show you this more in detail right now over here. This is the force and the deformation in function of time. The preload will be adjusted, oscillation will be started, and what you will find over here, the force is a sinusoidal loading shown over here, but if you have a look, the deformation is, so it seems, delayed. There's a delay between force, the sample excitation, and the response of the system, which is the deformation. I guess it's easy to explain. No sample like to feel a dynamic force application, a dynamic sinusoidal loading. The sample tried to avoid that by starting a deformation. But this speed of the deformation, how fast the sample can show this reaction due to an applied sinusoidal force, is related to the structure of the material, depend on the temperature, and depend on the load conditions, and of course on the frequency. And this is the difference between static loading and dynamic loading. The delay gives information about dynamic properties of the material. But why we need this? What's the benefit of that? This is what I try to explain under position number 3, dynamic testing, but why? Let's start with an elastic ball, a rubbery ball, which is able to jump easily. If you take the ball and let him bounce on the ground, it jumps back. Over here, there's a small mistake. The height, the initial height, of course, will never be reached by such a jumping ball. It should be a little lower. This is wrong over here. But you can imagine by slightly modifications of the material, taking the same polymer basic material, only use different kind of fillers. I will not discuss what kind of fillers are used over here. I can modify the dynamic properties drastically. This is shown over here. Now this is a ball having different fillers, and it jumps down, but it lays on the ground. It's not coming back. This means the mechanical energy stored in the system will completely convert it into heat. Energy will dissipating. With the same material, I can think over to perform a different test. This is a ramp, and a nice jumping ball is put on the ramp. We let him go down the ramp, and a nice rolling process starts. The rolling resistance of this material would be very low. The ball is rolling nicely. Completely different behavior has to be expected in case we are using the second material. Same ramp, same height, let the ball going down, and it stops after a while. Here the rolling resistance is much higher, but believe me, the materials are almost with the same hardness. So our hardness is very close of these samples, and the question is, can we distinguish these materials in a conventional universal testing device? Let's see what such a device is doing, and then we do a simulation of this test. Over here, this is a quite old picture of a quite old, 60 years old SWIC device. This is the load frame. The sample is clamped over here in the center. This is servo motor. This is a electromotor, and over here is a force recording system, and this is a paper roll for the strain recording. If you switch on the motor and the spindle is moving down, the holder is moving down too, and the sample will be stretched. The corresponding force, which increases with going on deformation, and the deformation itself will be recorded by the system. This is what this instrument is doing. Quite simple. Now, I have simulated this for you. Let us assume we span in first the non-rolling material under test. I told you show error is almost the same. If you put it into the system and start the test, with increasing deformation, the force is coming up. At the end of the test, at a larger deformation, sample will be destroyed. This is a destroying test performed with this kind of universal testing machine. Normally, from the initial state of the test, the slope can be calculated, and the slope is directly proportional to the stiffness or to the modulus. Now put in the same device, the second material, performing absolutely the same test, same speed, same length, and we are recording the signal like this. Again, the force in function of the deformation. A strain speed is adjusted, and at the end of the day, sample will be cut and will be destroyed. If you calculate the modulus, respectively the slope, we will find indeed for both materials, the result will be more or less the same. The slope 1 of the first and the slope 2 of the second material seems to be very close to each other, behave similar. In other words, a static tester cannot distinguish these nice properties we already have seen due to the jumping and to the rolling process. The question is, can a DMA do that? Of course, a DMA can do that. Let's start with the non-rolling material. What we are doing, you see this is the load structure of the high force DMA again. In the first step, we apply a preload on the sample. And here is shown what we call the damping, the time delta, the phase shift, the delay between excitation and sample response in function of the dynamic deformation amplitude. What we simply do with this test, we start a very small sinusoidal amplitude with 1 to 3 microns, and during the test we sweep the amplitude and increase them up to 1-2 millimeters plus minus. And as a result, you will find the damping shows a maximum number, indicating the mechanical loss in this material is quite high. If you want to produce from this rubbery material, for instance, a tire, your customers would not be very happy. Such a tire would have a very high rolling resistance. A car equipped with such tires would need a lot of gasoline. This would be quite inconvenient for for the customers. The second ball behaves completely different in the DMA test. Of course, the conditions are the same. In the first step, the preload will be applied and the oscillation will be superimposed. And what you find over here, the damping, again, in function of the dynamic deformation amplitude, shows a more or less strongly pronounced maximum, indicating a low damping, indicating really nice elastical properties. Producing a tire from such a material would save, of course, a lot of gas, but such a material, such tire would be not safe. Maybe you remember it jumps nicely. So in fast corners, car will easily leave the road. It would be, of course, very dangerous. Okay, that's the reason why tire people need DMA to optimize the mechanical properties of their, for instance, thread compounds between this extremely low damping material and the extremely high damping material. What kind of data DMA normally supplies? Okay, this is the viscoelastic response of the jumping ball. We already have discussed it. The final height we can obtain over here directly correlates to the storage modulus. It relates to the stored energy, the elastic reversible spring-like sample response. The E double prime, named loss modulus, directly correlates to the dissipated energy, and this is the viscous irreversible response of the material. These are elastical, these are viscous properties. In combination, we get the viscoelastic properties. Of course, these depend on the material, very clear, on the temperature, time, and frequency, and last but not least, on the load conditions. I will show you these later on. To make very clear what we are talking about, a DMA system is applying a sinusoidal force in function of the time. This is the amplitude, this is the time. The system is able to analyze the amplitudes and also is recording at the same time the response of the sample, which is delayed. Excitation is force, response of the sample, deformation is the strain, and this is delayed. Finally, we will find the so-called viscoelastic properties in the complex plane. On this axis is showed E prime, the storage modulus. This axis corresponds to the E double prime, the loss modulus. And for instance, a metal spring will absolutely not have any contributions in terms of mechanical loss. This would be more or less oriented to the E prime, whereas oil has absolutely no elastical amounts. So in all the materials we are talking today right now are in between an oil and a very elastic metal spring. This can be easily indicated with this diagram. I will not discuss the formula more in detail. You will find this information anywhere in any textbook of polymer science. Now coming to the force, high force DMA sample holder. This is a small selection. Let's start with a tensile holder. This is a self-tightening holder operating up to 1000 Newton. This is a compression holder. Here is shown a large compression sample. Smaller holders for smaller samples are available too. And maybe of interest could also be a penetration test. So for the upper load system, a needle type with a diameter from 0.5 up to 5 millimeters or even larger can be provided by GABO instruments. Over here you have the double shear system. This is a single dual cantilever, and very popular for the testing in DMA is also the so-called 3-point bending. Later on I will show you a few examples. Give me one moment, I'm back in 2 seconds. Okay, I'm back right now. Now, I promised to explain why high forces are so mandatory and so necessary. Let's start with a simple tensile test. Typical dimensions of tensile samples are shown over here. Here we have a thickness of 2 millimeters, maybe sometimes 1 millimeter is used. The width of the sample is 10 millimeters. In the range between 4 and 10 millimeters, you have usually to perform these tests. And the typical sample length is 30 millimeter. Now, coming with the first example. This is a polyethylene, this is a PEPA strip with a low density. Here I performed a temperature sweep with a heating rate from 2 Kelvin per minute. Frequency is 10 Hertz. The temperature range starts from -100 and is running up to +100 degrees C. On the left axis is shown the modulus on the log scale. Here we have 10,000 megapascal. And if you have a look on the behavior of the modulus, it starts roughly at 5,000 and comes down to roughly 200 megapascal. So there's almost a change by a factor of 10, okay, maybe a factor of 20 from here to here. Typical load conditions in DMA are a static deformation of 0.5% and a dynamic amplitude of plus minus 0.1%. Please have in mind the length of the sample was 30 millimeters. 0.1% simply corresponds to only plus minus 30 microns. The thickness of a human hair is about 80 microns, so it's indeed a very small deformation. I will not discuss right now about this nice tan delta curve, the class transitions of the different components. My focus is to analyze the modulus a little more in detail. Let's have a look. You see this is the curve. The modulus is about 5,000. Let's calculate from the geometry the cross-section. Easy task to do. We get a cross-section of 20 square millimeters. We have already introduced the dynamic amplitude of 30 microns. Okay, everybody, I'm sure everybody believes Young's equation, Young's formula. The strain is proportional to the stress. Proportional factor is the modulus, the Young's modulus. Okay, so we only have simply to fill in the numbers. Take the 5,000, put it over here, taking the square, the cross-section, put it in there, and of course the dynamic strain. If we do it, we will find out for the thin sample, the small sample, we always need a dynamic amplitude of plus minus 100 Newton. Now you should know the most a lot of instruments on the market are able only to run to 10, 15, 18 or 20 Newton or even 24 Newton. But even this would be not good enough to investigate this material. Now you could argue, okay, I can go to 1 millimeter, I can go to 5 millimeter. But on the other side, maybe you're also interested to investigate material properties at 0.2, at 0.3%. Okay, if I'm changing with this new geometry to 0.2%, we easily obtain 200 Newton. 0.3%, I'm going to the 300 Newton. So in other words, for solid state testing, high force is absolutely mandatory. Now having a look on a rubbery system, the same geometry. This is a rubber strip in tensile mode. Same frequency, same heating rate. At the static force 0.5, dynamic strain 0.1%. On the left axis again shown the modulus, but if you have a look on the curve, you see the strange behavior. This material shows a really high dynamic. What I mean by high dynamic, okay, the modulus is about 4,000 over here, but it drops down to 50, 60 over here. This is a very high dynamic. The stiffness changed by a factor of 1,000. Please have in mind for the previous sample, we have only changed by a factor of 20. Again, I will not discuss the tan delta curve over here. Now doing the calculation, same style, 4,000 is the modulus, cross-section is 20, the strain 0.1, fill in all the numbers in Young's equation, and last but not least, we get a plus minus 80. It's a little less in this example for deformations in this range. Let's discuss about a compression sample. Again, this is a rubber sample. Typical dimensions is 10 millimeter diameter, a length of 10 millimeter 2. This is a typical small specimen for DMA testing. Please have in mind, in DMA, you are able to change the temperature very quickly. Rubber and the most polymers are bad heat conductors. If you increase the size of the sample too much during a heating scan, from minus 100 to plus 100, the sample cannot follow that speed easily. That's the reason why we normally are restricted to quite small samples, having a diameter of 10 and a length of 10 millimeter 2. This is again the curve. You see, conditions the same, 0.5, plus minus 0.1, 10 Hertz, 2 Kelvin per minute. Compression sample. Modulus is always the same. Rubbery materials show a modulus always in the same range of 4, 5, 6,000 megapascal. Okay, doing the calculation. Same style as before.